Hey guys, I realize I'm slightly an idiot because I've been streaming to Twitch for the past minute. I didn't even realize it wasn't going here. So that's kind of fun. So yeah, this is a good start. Anyway, what I was saying to nobody apparently is that I was sad about. Actually, wait, is it working on Code Forces? Oh, it's like glitched. Yeah, okay. Let me put this back up. It's not finished, so I'll do that. Yeah, okay. But anyway, the way these notifications work is that like you this plus 149 thing that I've had for like 3 months is just gone, and I'm really sad about that. And the way these notifications work is that like it's based on this thing, this share it. And so if anyone clicks on this, not even myself, if anyone does it, the notification will go away. Which is annoying. Like, what kind of design would have it so someone else clicking your notification would make it red? It doesn't even make sense. Anyway, the plan today is to finish this. I haven't added the hard problems because I probably wouldn't get to them in time. So, let's see. Let me link this. Where do I go? I gotta, like, do some stuff. Send it out to the Discord. Okay. Yeah, there's also, like, this top coder thing going on. So, oh, the share it thing, like, there was this, if you go to any of my previous videos, you'll see this message, like, you have plus 149, wow. And then it just went away. I'm not gonna say your name if you put that in the message, where, no. Can't, like, combine that. See, Crystal Violet has a normal message, so I'll say their name, sure. Okay, wait, what was I saying? I'm not actually sure what I was saying. Yeah, there's this like top coder thing going on, and it's like a bunch of things, so you could like that exists too. And if you want to see that, that's fine because this stream is going to be up as an archive anyway, so you won't really miss anything. Okay, so as it turns out, I got one of these problems in a duel, and I like solved it accidentally, even though I haven't solved it on this, which is like stupid, and I didn't realize that. But the good news is I didn't actually solve it with DP, so I could use the DP approach to solve it in a different way, and therefore it'll be like I haven't solved the problem yet. So we'll think of it like that. Because the way I solved it was something else. So I'll force it to be a DP approach, and then it'll be a different problem. Yeah. Okay, anyway. So in terms of the plan, I'm just going to go through these problems. Wait, actually, let me check and make sure everything's, like, set up right. You guys can see, I'll get rid of the poll. You guys can see the mashup link and the previous stream here in case you missed something. No, you get ignored because of what was in your message. Okay, so do you guys remember last time, the last topic stream where I spent like 5 minutes trying to pin a message? Well, it turns out I just unlocked that, like a week or so after the first topic stream happened. So I was right. It wasn't possible to do it yet. But now it is possible. So I think I can do it like this. Current problem I, and then I can pin this or something. Yeah. Alright, you see? So now you can see the problems that's like actually happening. Apparently not on mobile though, so have fun with that. I don't know. Does this work? It should work. Fine, I'll say your name. What's up, Sophie? What's up, Sam? How are you doing? Okay, it's time to actually start. How far are we into this stream where I haven't actually done anything yet? So this first problem is called Problem I, Mike and Fun. Mike and some bears are playing a game just for fun. Alright, in terms of the pin, like, the pin was, like, it said I just unlocked it. Like, I opened the streaming window, and then, like, right here or so, it said, new feature, you can now pin messages. So I wasn't able to do it before, but now I have it. I don't know what made me get it, but, it's working now. And actually, I'm gonna, remove that and make it a link, so you can open it straight from here. And I'll pin this one. Okay, does this work? I hope so. Yeah, okay. Yeah, they saw me try really hard for the pin. Alright. Alright. Mike and some bears are playing a game just for fun. Mike is the judge. All bears except Mike are standing in N times M grid. There's exactly one bear in each cell. We denote the bear standing in column J of row. Yeah. Mike's hands are on his ears, like it's a grid. Row I, column J. Mike's hands are on his ears since he's the judge, and each bear standing in the grid has hands either on his mouth or on his eyes. Okay. They'll play for Q rounds. In each round, Mike chooses a bear IJ and tells him to change his state. So if his hands are on his mouth, eyes, or eyes to mouth, after that he wants to know the score. And the score is the maximum over all rows of consecutive bears with hands on their eyes in that row. The bears are lazy. Mike asked you for help for each round. Tell him the scores of these bears after changing the state of a bear selected in that round. Oh, I see. Okay. Sure, I can see how this is DP, I guess. Wait, does it change permanently? Does it change permanently, or is it a single operation? I guess it would. I guess it would change permanently. Yeah, okay, so I guess this is the idea of the problem, that you have this grid. Let's use the sample. And you have 5 rows, and then in this grid, you have some 1s and 0s, as the problem gives. Okay, so use orange for 1. That's what it is, right? It's this type of thing. Then everything else is 0. And then what you're interested in doing is, I suppose you want to make it so or rather you'll do something like this, I guess. Wait, what? I don't understand. So it's 1 1, okay, 1 4, 1 1, 4 2. Okay, so basically here's the idea. For each row, independently, find the longest streak of 1s in this row. That is like the longest consecutive group of 1s. So for example, this group is 1, this group is 1, and this isn't a group of 1s, so it wouldn't work. So in this row, the answer would be 2 because you have 2 1s in a row. In this row, the answer would be 1. This row, the answer would be 2. This row, the answer would be 1. And this row, the answer would be 0. And then over all the rows for this value, you want to take the maximum of these. And that's your answer for a query. Yeah, the mic is bad, I know. I don't have a fix for that right now. This is just my laptop mic. Oh wait. Okay. Sorry. This pin message will let you link the thing, but to open the mashup, you have to click this in the description first, and then it'll invite you to the contest, and then you can open whatever you want from it. Yeah, you have to be invited to the contest first. You can click that link in the description. Yeah, I'll upload the video later. So if you want to watch Top Coda right now, that's like fine. I won't stop. Obviously, I won't stop you, but this will be available later on. So if you miss this, it'll be there later. Yeah, just like the last one. And in fact, you can also find the last one in the description if you missed it or something. Oh yeah, by the way, I forgot to do this. I'm going to update the subscriber count because that's a normal thing we do. Okay. And so each query is basically you change a single thing. You change a single cell either from 1 to 0 or 0 to 1. Now, I guess the idea is if you have 5,000 queries and N and M are 500. So if you were to change it and then recompute this whole thing every time, it would be 5,000 times 500 squared, which is too big, I suppose. Might actually pass the time limit, but it seems too big. Yeah, so in brief, the problem is you have this grid of ones and zeros. For each row independently, find the longest streak of ones, like the longest consecutive group of ones. And then over each row, take the maximum of these longest groups. And then that's the answer for a query. And a single query is changing a single value either from a 1 to a 0 or a 0 to a 1. Yeah, so the basic idea is like, consider that we do it for each row independently. Then if we change something in a single row, like it only changes that row. None of these other values change. That's the basic idea. So if we change it for a single row, we only need to recompute the value for this row. So this is O of M, the number of columns. And then this value can also change. For example, after this query, this value become 2. And then we can just like take the maximum over everything once again naively because we only have O of N rows. And so each query would be, each query would be N plus M instead of N times M, which is much better. I suppose that's the idea of this problem. So how do we compute this? Well, we just need to solve the 1D problem of what's the longest group of ones. And to do that, we can, this is where the dynamic programming comes in, I guess. Let the, let's see. How would I word this? Let the value here, actually wait, we're doing this dynamic programming style. So first, let's identify what we're even trying to compute. We want to find the longest group of ones in this array, right? So one way to do that is to fix the ending point of the groups of ones, and then find for each ending point, like the leftmost point where there's still a group of ones. And that will give you the longest group of ones that ends here. So that's the goal. Instead of doing it overall, just do it for like a specific, like an ending point all at once. And so you can define a function f that takes in index I, and it's the longest group that ends at I. Hear my mouse clicking furiously. So f of I will be the longest group ending at I, group of ones. So if this value is a 0, then like this just is 0, because you can't have a longest group that ends here if there isn't even a group at all to begin with. There's just no ones here. So if AI is 0, then f of I is automatically 0. Otherwise, either you have this individual group of ones, or you can do better, you can extend some previous group to the left, and then have this be the end of that group. So now, instead of finding the longest group that ends here, we're still doing that, but we're interested in the longest group that we can extend from the previous index. And of course we want the longest group, so it's the same as asking what's the longest group that ends at the previous index. which is literally what f of I is. And then we add 1 because we're extending it. So if we have a 1, then it's equal to f of I minus 1 plus 1. Because we're extending some group that ends before here, and then we're adding 1 because we stick on this 1 to the end of it. So the longest previous group is just the definition of f of I minus 1, and then we add 1 because we stick on this 1. So those are the possibilities. And this is sort of DP-esque because it's building off of previous answers. In fact, it's similar to like the second problem or something. Pretty sure that's what it was. So, I suppose that would be it. Yeah. So we compute this, and then like the answer for a row is just the maximum over all f of I, because we're like solving for all ending points, so we have to consider all of them. Right. So here we do this for every row, and then we get this value, and then when we get a query, we only recompute it for a single row. So let's do that. Let's see. So we store a best array of size like bigger than n, and that will give you the best in each row. NMQ. Read in the queries, then just like do the stuff. I can't type. C into. Yeah, I did do the sub count. It's up to almost 5,000 now. So now I'm going to make a function called solve row. Because each row is independent, we can just kind of like do it independently. LL, let's see, this would be the row index I. Then LLF. We basically compute this function for this row. So I'm set, all right, f of 0 equals 0. This is just for implementation convenience, since that way, like this value for f of 1 would be like simple. Oh yeah, if you can't access the contest, what you have to do is you have to click this link first, because it makes you open it. Yeah. Wait, I can't edit messages. This is annoying. I'll make that clear the next time after we finish this problem and I pin the next one. I equals 1, I is less than or equal to m, I plus plus. We're going to compute this f value. So if mat I, this should be j actually, j minus 1, this is the value at this row in the matrix, just like this. If it's equal to 0, f of j is equal to 0. Otherwise, we use the recurrence. So f of j is equal to f of j minus 1 plus 1. And then we keep track of the maximum over all f of j. And then we say that the best value in this row is equal to the answer. So now we initialize it like this, and then for every query, we only recompute a single row. So therefore, we only need to call solve row once for every query. So what do? We read it in RC. Then mat RC is flipped. We can say that's like XORed with 1. Yeah, it's not exactly DP. I mean, it's kind of a stretch, but you can call it that because it still depends on previous subproblems. So mat RC is XORed with 1, which basically means just flip it, 0 to 1, 1 to 0. And then, so we resolve the row for R, and it's equals 0. Then for each row, ants equals max ants best j. And then I'll make the rest of these j too. In brief, figure out the value for each row. Then this is just taking the maximum over all of them. Nope. Go to the directory first. And so, seems right. Let's make sure. Read in the values, read in the matrix, solve the rows initially. Read in the values, solve the row. Like resolve the row because we changed it. Like find the answer and compute the values for each row. Some of these aren't exactly going to be DP. I mean, you can do that one with something like 2 pointers. Also, but you could argue a DP solution for it. Okay, this one is like the least solved, which means it's probably going to be fun. So here, let me unpin this current problem J. You can send problems after if we have time, but right now, no. Or right now, I'm like not doing requests. Current problem J. Right. And I'll pin that. Hopefully it should work. Yeah, okay. Helga Hufflepuff's cup. I can speak. TMW ors. I agree. Okay. Harry, Ron, and Hermione have figured out that Helga Hufflepuff's cup is a Horcrux through her encounter with Bellatrix Lestrange. What do you consider as better? Because like big techniques that aren't used very often are like annoying. I don't know. Anyway, I'm not sure how these problems are yet, so perhaps not. Okay. Through her encounter with Bellatrix Lestrange, Hermione came to know the cup is present in her family vault. Right. The Wizarding Bank is in the form of a tree. Oh, interesting. With total n vaults, where each vault has some type. A tree is an undirected connected graph with no cycles. The vaults with the highest security are of type K, and all vaults of type K have the highest security. Okay. Also, if a vault is of the highest security, its adjacent vaults are guaranteed to not be of the highest security, and their type is guaranteed to be less than K. Interesting. And there can be at most X vaults of highest security, and X is at most 10. What the hell does this mean? So, Harry wants to consider every possibility. What? Oh, okay. Every possibility so that he can easily find the best path to reach your vault. So you have to tell him, given the tree structure of Gringotts, the number of possible ways of giving each vault a type so that the above conditions hold. This is weird. Why K? Why not just like M? That's annoying. Okay, let me read the rest of the constraints and make sure I have this right. So, this is annoying, isn't it? Alright, let me get rid of the scribbles. This is problem J. I'm going to put that here. This is problem J. And yeah, I just started another problem, so it's not that big a deal. You have a tree here. Let's say something like this. I don't know, make it deep because it kind of has to be. right? Some sort of tree, and you want to put some labels on this. So you want to put some labels so that each label is at most m, and there are wait, exactly or at most? At most x vaults that have, or at most x nodes that have label k. And then another constraint is that everything that's adjacent, if you say this thing has label k, then like for some reason, first of all, you can't have adjacent things that are k. And also everything adjacent, so like this one and this one, has to have a value less than k. So this is less than k, and this is also less than k. So given these weird constraints, you want to figure out how many ways it's possible to assign labels to fit these constraints. Okay. So this is a DP contest, and therefore we're going to use DP. And the way we use DP is kind of like weird. I'm pretty sure it is. Pretty sure it's some sort of knapsack thing. That's my idea. And I'll tell you where that comes from in a sec. So the basic idea is we want to find some state for this DP. And the classic sort of tree DP state is some subtree. So for example, what's the answer for this subtree? Okay, convex hull trick is like not suitable for this stream. I'm barely getting into tree DP right now. If you wanted hard DP, more people should have voted for that. So yeah, convex hull trick is hard. But anyway. So for some classic tree DP problems, you essentially want the state to be some sort of subtree. So that is, what's the answer considering only this? The people want me to continue this mashup. That's what the vote said, supposedly. Yes. Well, also because it's going to get me the most views. That's like how it works. So solving for this subtree only, what's the answer? Communism? Like giving the channel away to everyone? For this subtree, what's the answer? That's a good question. It turns out this isn't enough, because like there are multiple possible things a single subtree could represent. Like for example, this could be a thing of node k, in which case we have this constraint that this has to be less than k, specifically. But at the same time, that's equivalent to this not being a node that has k, and this could be the node with k, and then this can be anything. But if we only store the subtree information, then both of these are equivalent, so we don't have enough information. So what we need to do is we can't only store the subtree as a state. So for example, say we're trying to build this DP formulation where we have DP of V. That is, for this vertex V, what's the answer for it and everything in its subtree? And it's not rooted, but we'll just like root the tree arbitrarily at node 1 or something. That makes it simple. Then we're interested in everything in this subtree. The number of ways in this subtree, then somehow we combine children. Okay, now the basic idea here is that we need more information than just the vertex. What else can we do? We need, well, for example, one of the distinguishments we need to make is that is this node value k or not? Because if it is or it isn't, that affects what we can do to this node. So we need another flag that basically says, is this node value k? So dp of v and also, what do I call this? Like a flag or something. But then there's also something else, because we need to make sure that we only have at most, what is it, x of the vaults. we need to make sure that we have at most x of the vaults, right? So if we have two different subtrees, like say we use 3 vaults here, and then we use 1 vault here, and then like the total x is like 2 or something, then that's a problem. We can't do that. But like if we only store this information, then using 3 vaults here is an equivalent state to using only like 1 vault here, for example. So with only this information, we can't determine how many vaults we made, which means we also need to store not only this and the flag, but also the number of vaults. So it's v, the number of vaults, and this. A flag representing whether this node is k or not. And I claim that this is enough, like this is enough information, because TMW dislike because I'm better than him. I made this diagram in my Discord that shows like how rare the beating him in Kickstart thing was. So if you join my Discord, which is in the description, you'll be able to see that. You know, by the way, it's time to plug the Discord here. Right here, you can join it, and then it'll be like annoying, and the Discord's terrible, so everyone can cringe with me. That's the idea. It's like an anti-plug. Alright, so whatever's happening here. This is enough, because the only thing we care about, first we have to care about the vertex. No, there is a strong comparison. Like, he's just better than me. A lot. In many ways. I will admit that myself. Right. So, and then we need the number of vaults here, and then we need a flag. Now, in terms of the problem statement, like, the way to get the state is usually to determine what we need from the problem statement. From the problem statement, we have a bunch of constraints. We have at most x vaults, and we have the adjacency constraint. But there's nothing else. So there's like no other kind of information we need to store, because the problem statement says this is enough, since there's no other information the problem statement requires us to have. So that's how we can tell what a state should be. It depends on the constraints of the problem. Because we have the constraint that we can use at most x vaults, we have to have that in our state, because that's a constraint of the problem. Because we have the constraint that adjacencies like make things weird, we have to have that in the state, because that's part of the problem. That's the idea. I'm not the GOAT. Like, by definition, I'm not. You could, like, sum up the number of times TMW has beaten me and the number of times I've beaten him, and it would be, like, 10 to 1 or something. Like, you can't say things like that yet. I'm not that good. Compared to him, at least. That thumbnail was strictly a joke. Okay, how's this gonna work? So, well, my Discord is terrible. Alright, how's this gonna work? So, the transition seems fun here. Because there's like... Alright, how do we do this transition? This is annoying. We have this node here, and what we want to do is, like, say we're solving for this node, we need to combine the answers of the two subtrees. So let's say we have an arbitrary number of subtrees. Then say we're trying to compute dp of A and B. Or, like, let this be node V. Then we have dp of V and A and B. So the question is, like, how the hell do we do this, all right? And actually, a better question is, how the hell do I explain this? we have, essentially we can take any number of things from here, here, and here. But so the idea is, it's casework. Say we have this flag be 1, which means we're going to make this equal to k. Then that means like the only states we can use are ones where none of these are equal to k, otherwise we would have the adjacency condition. Then this is even more annoying than I thought. Okay, there's actually I was wrong. There's actually more we need to store. I did. I insulted Discord. So because there's something here. If we're going to make this k, then if we're going to make this k, then what we need to do, or sorry, if we're going to make this k, then we have to have the constraint that all of these values are less than k. Because otherwise it wouldn't satisfy the problem statement. So this is more annoying than I thought. And I already thought it was annoying enough. So this flag actually has 3 possibilities. It's less than k, it's equal to k, or it's greater than k. Because all of these are all of these like matter. We need this kind of information. So we need 3 different things. Okay, I have to figure out a way to explain this transition that like actually makes sense. So transition is assigning less values to subtrees from the current node. No, it's like we're sort of given the values that we put in these subtrees, assign a value to this one and find the number of ways. Like we know the answers for these subtrees, and we're trying to figure out the answer for this big subtree. So we assume that these subtrees are already predetermined, and therefore the only thing that we can change is this one. So this is like really annoying. This is very annoying. Very annoying to explain. I'm sorry for this. Well, it also matters if it's less than k or not, because if it's not less than k, then we can't put a node right above it. So there are 3 possibilities. A node is less than k. Actually, let's solve for that. This is going to be the hardest part to explain, I think. So I may have to reiterate because it's kind of confusing. Say this node is going to be less than k. So its value is going to be less than k. Therefore, this state is going to be 0. Actually, implementation isn't going to be terrible. The worst part is explaining this right now. I think that's how it is right now. So this value is going to be less than k. How many times have I said that now? So that means whatever, these values can be anything really. Because the less than k means that this can also be less, like this this node, it can also be less than k because that's fine. It can be equal to k because it's allowed to do that, because this is fine. And it can be greater than k because it's also like chill. So therefore we're allowed to take from anything x, comma, actually not x. Let's say another node y, comma, another node, another value like c, and then anything. So a star would mean that all possible values work. And we need to pick some values out of this to like make it so this sum is equal to a. So if you see sort of a similarity between, let me try and rephrase this. So what this is saying is to find the number of ways to have it so we've used less than A things is equivalent to saying how many ways are there to essentially like, for example, we know how many ways there are to use two what would they even call it again? Two high security vaults like that are equal to K in this one. Let's say we have a D number of ways. And we also know, for example, how many ways we can do it here. 1E and like 0F or something. And we know that for all of these. So we're trying to find the number of ways we can pick some of these values that sum to at most K. Or at most X, the parameter X of the problem. And so I'm not sure if you see the relation here, but this is knapsack. That's what this transition has to be. We have a certain cost and a certain number of ways of choosing that cost, and we want the sum of costs to be less than a given number, or less than or equal to a given number. That's what knapsack is, kind of, in a sense. It's like it's not exactly knapsack because it's not the sum of costs, but it's a similar kind of number of ways thing. So within this transition, we have another DP problem that we have to solve. And that's what makes this so annoying. That within this transition, let's say we sort of like tack on these nodes in order, in some order. Then we have this other DP recurrence. And use a different color, I suppose. We have this DP recurrence. What other color do we have? So DP of, I'm going to say U. U is the current node we're at in this list of nodes that we're going through. What? What is happening in this chat? Okay. We have DP of U and the current number of things we've taken. Let's call it Z. Or wait, DP of U and the current number of like these things, the high security vaults that we've taken. And so the transition would be, when we have this, we consider all the possible values. And then we say, for example, if we have the state like 0 and then F, then this would add to we would essentially like, this state would push out to the next value, and then also the number of taken because we don't take any more. And then we multiply that by F. And the same kind of thing here, if we have this state 1 in E, where we have E ways to make it so we take exactly one thing, then we have this like goes out to U plus 1, and then the number of taken, but we have another taken one. So now it's 1. Should we have slow mode? Is it necessary? I don't know. And then for all of these possibilities, for all of these like number of things we've taken, we sort of push this DP out to future states. Or we can do like whatever kind of DP you want. It doesn't really matter. It's just like this recurrence. So the number of ways to be at the next vertex, having taken one more than we just took here, it's the number of ways we can take one times the number of ways we can do the rest of it. So it's going to be, for example, the value E times this DP value will be added to this value. So it's very similar to knapsack. Very, very similar. Have we even seen a knapsack problem on here before? I'm not sure if we have. Do you guys want me to go over knapsack too and what that is, or is that well known enough that I don't have to? Because knowing knapsack will make this transition make more sense, because it's very similar. What do you guys think? Is anyone alive in the chat? Vote is 1-1 right now. Anyone else? Three to 2. Okay, it's like very even right now. You know what? For the purposes of education, I'll just do it. Or wait. Yeah, okay, I'll do a quick overview of it. It shouldn't take that long, probably. So the idea with knapsack is we have a bunch of items. We have a bunch of items that have a certain number, a certain weight. Like for example, 2, 3, 7, 5, and they have a certain cost to them too. So for example, 3, 7, 1, 2. And essentially, we have this like total capacity like 13 or something. And we want to pick some subset of these items to maximize the sum of their costs. So for example, the sum of these green values. And simultaneously, their total weight must be less than or equal to this capacity. That's the problem of knapsack. The way to solve it is essentially dynamic programming. Our state is, what's the best answer we can get given that we've used the first I items and that the total weight or the total capacity we've used so far is J, for example. Then the transition is simple. For this next item, for the I plus 1th item, you either take it and then you get like, what is it? So let this be the cost and let this be the weight. Then Ci plus dp of ij will kind of like this value dp of I plus 1, j plus weight, j plus the weight of I. You consider this value in that. So you can think of it the other way too. The dp of I plus 1j relies on dp of I and j minus wi, if you prefer to think of it that way. And then like the basic idea is just that this is the information you have, and when you take this item, this information gets changed. So you go to the new index, and at the same time you have a new weight, specifically the weight you gain from taking this one. And so you can also just not take the item, and then in which case you have dp of I plus 1 and the same weight. That's the essential idea of knapsack, I suppose. If this notation doesn't make sense to you, you should probably see the first topic stream. Knapsack with weight capacity up to 10 to the 9th. That is interesting. Are there any other constraints, like the @coder one? I'm pretty sure there's like some weird solution for it. Like I remember seeing some Codeforces problem, but I don't remember what it is. So I'm not sure. It's some divide and conquer kind of thing. Oh, by the way, the answer would be dp of n, where you consider all the items, and any j where j is between 0 and the capacity, that is 13. You would consider that because you can have any capacity as long as it's less than 13. Okay, well the @coder one is different because the @coder one has the I'll pull this up later maybe, but the actcoder one has the other constraint be tiny. Like the costs are tiny. So you can formulate it as thinking of the minimum weight to obtain a certain cost, and then see if all of those are possible. What would default weight capacity be? Okay, anyway, that's knapsack in brief, kind of. So this is sort of a similar thing, except we're counting the number of ways instead of minimal cost. So either we take this certain number of items, or we just don't. And so if we do, then we get a new sort of capacity, and if not, then we just simply don't take it. That's how you would do these transitions. Now this is only for 0. Well, actually, sort of, no matter what you do, you want to get these values. Like you have this many ways to make it so you've used 2 things. You have this many ways to make it so you use 1 thing, and you have this many ways to make it so you've used 0 things. And then this final value, all these will be multiplied by the number of ways you can have a number less than k, which is to say it's k minus 1. Okay, now this is one case. The next case is if this value is 1, in which case this value is equal to k. I'm going to cross this out instead of erase. Actually, no, I'm going to erase. In which case this value is equal to k. And then there's some other stuff going on here. For example, okay, now what does this mean about other values? What it means is that all of these values below, like this one, and this one, by the constraints of the problem, all of these values have to be less than k for this value to be equal to k. Otherwise, like that's just what the problem says. If you have this k here, the adjacent ones have to be less than k. So what that means is that the only states you can consider for previous ones are ones where it's less than k, so therefore the flag must be 0. Right. And then that's essentially how this would work. And then there's only one possibility for this value, it's equal to k, so there's only one thing you multiply the knapsack by. And how bad are these samples? Oh my god, they're all size 3. What the hell? Oh, this is going to be so painful. And, okay. Well, there's one final part. The final possibility is that we have greater than k. And therefore this flag is 2. So then the possibilities are, well, none of these can be equal to k because the problem statement won't let them be, since this would have to be less than k for that to be true. So these can be either less than k or equal to k, or greater than k, because either way that's fine. So the constraint is that it's not equal to k, which means it would rely on the states 0 and 2. And then the number of possibilities would be, what would it be indeed? It would be m minus k. That's the number of ways to have that happen. So in total, if the flag is 0, then we multiply by k minus 1, because that's the number of ways we can make a value for this one. And then we rely on previous values dp of any y, c, and 0, 1, and 2. If we have flag 1, then we have exactly one value, because it can only be equal to k. And we rely on the previous values dp of y, c, and 1. No, 0. Every value has to be less. And if we have 2, then we have m minus k possibilities. That's just the number of numbers greater than k. And then we rely on dp values y and c and 0 and 2. This is organization for myself, because now it's time to write the code for this. How fun is that? I am almost certainly going to get wrong answer on this one at some point. So that's fun, isn't it? All right. So all of this is preparation for the implementation. Let's do this. Okay, so first, we read in the values. Vector edges up to 10 to the 5th. Then for each edge, edges u dot push back v, and do the same. Yeah, it's definitely gonna be fun. Now, C into k into x. So now we define this function DFS, a vertex and its parent. So here we would DFS from the root 0, and then the parent would be nothing. And then, okay, I'm gonna do everything except for the DP part first. So the final answer would be, well, we actually don't care about anything here. What we really care about is any value, any value that's between 0 and x, and this can be anything. So the final answer would be, what's the modulo? Yeah. The final answer would be dpij mod mod. Now the question is, how do we do this? All right. First, we define the dp. We need one for every node. Then we have at most that many possibilities from 0 to 10. And then we have 3 possible flags. I'm going to make this slightly bigger just to be safe. Doesn't actually matter. All right. First, for I equals 0, I is less than, no, what? For each child, edges b. If x is not equal to p, then DFS xb. So initially, we have this state. dpv, let's do this better. Topic stream may or may not be a weekly thing. Okay, so the way the topics work is, I know YouTube kind of sucks and this setup is terrible, but the way people actually vote on topic streams is I have this thing called a community tab, and then there are polls here. But for some reason, if you're not on mobile, it doesn't tell you about this. So this is where the polls are, so you can vote here and stuff and stuff. But apparently it doesn't tell that to most people, which is really annoying. That's why I want people to join the Discord so that they can get notifications about stuff like this. And you can join the Discord here. So it's yeah, it's weird. It shows you community posts on mobile, but you can't see the community tab. It doesn't show you the posts on here, but you can see the community tab on here. I'm pretty sure it's just an absolutely terrible system, honestly. But yeah, topic streams will occur sort of pseudo-frequently. Now, join the Discord only for notifications. You don't have to chat. You definitely don't have to chat. In fact, I don't recommend chatting. Don't recommend chatting at all, in the least. So what's the idea here? That 1 second. I did send that. Okay. Right. Sorry. So the idea with this is that we have to do this. I'm not joking about the Discord. So we have to do this sort of sub DP. And basically this value is at most x, and this value, all right now. Let's see. So LL sub DP. And so this value is at most the number of children of this, which sums to O of n in total. So the number of children is upper bounded by the number of adjacent nodes, the degree. So we can do like edges v.size plus 1. And the other value is at most x. So it's x. Then we set it to 0. And we say, if we've taken nothing, then there's exactly one way to have it so we have taken no special nodes yet, and we haven't considered any nodes yet. So alright, this is fun now. So first, wait, how exactly are we doing this? Okay, actually, I guess we're doing this for like each individual thing. Alright, there's some way to implement this, and there's some way to implement this that I do not know of. I think we do this sub DP 3 separate times, I guess, for each possible flag. So let's first do it for flag 1. I'm going to do this sort of scope magic to make it so I can declare this every time without having to, actually no, I don't need to do that, I guess. Yeah, I can just do memset, I suppose. Although I'm still going to do the scope magic because it's kind of convenient. Then, for every subtree, what we do is, for LX edges V, if x is not equal to p, count equals 0. Now what we have to do is we have to push these values out to the later ones. And so the way to do that is to first, we have to fix the number that we've taken. So taken is equal to 0, taken is less than or equal to x, then that, consider all of them. Then we also consider what do we consider? Yeah, I know like top code is going on right now, but I'm doing this now because I don't have any other time to stream this week. It's like it just has to be inconvenient. It's kind of annoying that way. I didn't even realize top coder was going on until yesterday, but I don't have any other time anyway. Yes, we can root at any node. It doesn't matter. We just need to have some sort of way of defining a subtree, and that's why we root in an arbitrary node. Oh, by the way, this scope magic is basically saying like you know how you have for loops, right? And these kind of just have their own scope. Well, I'm doing this, but without any sort of loop. So it defines a new scope, but like for no reason, kind of. Except the reason is so that it can be its own sort of thing. Okay. So right. For L occur taken equals 0. I have yet to figure out the complexity of this program. How is this a 2000? I don't understand. So then this is the number we're going to take. If cur taken. Yeah, I use it so you can use local stuff, except I'm not actually doing local stuff, so nothing really makes sense. But I'm going to basically copy the same code 3 times, so that's why I'm doing this. Just so there isn't any sort of copy paste error. Total equals the number we've already taken plus the amount we're about to take. If total is less than or equal to x, then continue, and say that. And actually, if not, then we can break because we know that like this is only going to increase. Or actually, we can say take is less than or equal to x minus cur taken, and that works too. So we don't actually have to check this. LL val is equal to. So for this flag, we define it like this. Because we make this value less than k, we can have it so any of the previous values in the subtree can be anything. We don't care what they are. So it can be 0, 1, or 2. So therefore, it's sub dp count 0. Actually, how does this work? It wouldn't be sub dp. No, it would be dp of x, and then take. No, okay, this should not be x, my bad. This should be something like y, the new node that we're using. That's a bit confusing. So this should be y, this value should be x, this value should be x. This is the child node we're considering. And it's this plus y take 1 plus dp y take 2. And in fact, this is the only value that's going to change in the 3 things I'm copying. But I don't see a better way to do this. So I'll just leave it as so. Then how would you do this? Then be the new sub dp count plus 1 and take and no wait. This would be the total. This is the new amount we've taken. Equals sub dp count plus 1 total. Plus the value, the number of ways we can take this many things from this node, times the number of ways we can take it from like the previous configuration. Or like the number of ways we can take it from the first this many nodes, and then times this one. Which would be sub dp of count and the current number we've taken, mod. What? Right. Let's sanity check this. So this is the current amount we've taken. We ensure it's less than or equal to x. This is the amount we're going to take. We ensure that this sum is also less than or equal to x. Then the value we have is simply all possible things we could have taken from this node, because this value is going to be less than or equal to k plus 1. And then this is going to be this. It's the number of ways to take it from this node specifically, times the number of ways to do it from the rest. Seems legit. Okay, now we do the final parts. For LLI equals 0, I is less than or equal to x, I plus plus, sub dp count I equals sub dp count I times k minus 1. And this is necessary because there are k minus 1 different values we can have for the current node that we're at. This can be any of k minus 1 different values if it's less than k. So, and then somehow we do this here. Then we say, actually this doesn't even have to be sub dp. This can just straight up be dp of v I, and the flag would be 0. Because that's what we just computed. Okay, that is painful. But that's the worst of it, I believe. So now it's almost the exact same thing, except we changed like 2 lines or so. And so if I end up getting this wrong, I'll have to change everything all again. So if we're going to make this value equal to k, then there's only one possibility for this value. And the other thing is that we're going to only rely on the values that are less than k, because we can't have it be adjacent to anything else. So this is that. And then the next value is flag equals 2, where we have, we can rely on anything that isn't equal to k. Y take 2. And essentially, now this is going to be, the number of values is m minus k, because that's the number of values greater than k, but less than or equal to m. Right. And then this should be 2, and this should be 1. And I suppose that's it. Oh, I should increment count. This count is the number of nodes that are not parents. And I can't do a normal for loop because the parent could be part of this adjacency list, and I have to skip it in that case. Alright. Let's try it. Ants equals ants plus dp 0, the root node. I'm gonna have to test this with some stronger samples. Okay, it's wrong already. Great. What else does it work for? Does it get 0 at least here? It does. Okay. Right, so what the hell is this sample then? We got 3 nodes. Like, we failed a sample of size 3. How sad is that? We got 3 nodes. 1, 2, 1, 3. And we can have the value of k is 2, and we can have at most 1 thing. So what exactly is happening? Now we debug. I1xj. So essentially, how many ways does it think we're finding for each node? Oh, right, wait, what did I do? Yeah, okay, so actually, I forgot that this is like, this transition makes another node with k. So therefore, this has to be that we take 1 more, which I kind of forgot about. So I'm actually like not sure how it did this at all. Yeah, that I don't understand. did that work? How did that work at all? Okay, normally in contests I would use stronger samples to test this, but because this is like YOLO, whatever, I'm just gonna submit this. It's probably gonna be wrong, so I'm gonna try and come up with more samples. Oh, we actually got it. Wow. That actually worked. Is the stream buffering? Oh, come on, OBS. What the hell? I believe in this. Alright, well that was that problem. That sucked. Let's do something better. Let's see. Okay, so I've done... What have I done? I've done this one. I have yet to do this one with DP. So, yeah, okay, I guess OBS is just glitching sometimes. I have yet to do this one with DP. So, well, I'll try and do the DP solution for this. Alright, that was J. Now this is problem L, and I will edit this message. Let me click this. This is going to be problem L. Can I edit this anymore? No, I can't. Somehow I'll find a way to be more organized about this, but not yet. Okay. Suppose that's cool. Okay. Innovation techniques are on a victorious march around the planet. They integrate into all spheres of human activity. A restaurant called Dijkstra's Place has started thinking about optimizing the booking system. There are N booking requests received by now. Each request is characterized by two numbers. CI, the size of a group who will come via this request, and PI, the total sum of money they will spend in the restaurant. We know that for each request, all CI people want to sit at the same table and are going to spend the whole evening in the restaurant, from the opening moment at 18 o'clock to the closing moment. Okay? Unfortunately, there are only K tables. Each table has a maximum number of people that can sit at it. Each table can only have people from the same group. That's nice. If you cannot find a large enough table for the whole group, then all visitors leave and naturally pay nothing. Your task is decide which request to accept and which request to design so that the money paid by the happy and full visitors was maximum. Now, I told you, I have solved this problem in a duel, but the way I did it was with a greedy, and it was, like, not good. So, I'll use the same principle, but we'll do dynamic programming with it. So I will show you how you can use dynamic programming to solve this problem. And really, like, even if a problem... Like, even if the main solution of a problem isn't DP, if you can still apply DP to problems that aren't, like, obviously DP, and if you can still make that sort of, like, thinking and do that sort of thing, then you'll, like, definitely be able to apply to problems that actually are DP. So even if a problem isn't obviously DP, you can still practice it by trying to use the technique on it. That's why even though some of these problems aren't necessarily DP problems, they could still be useful, per se. I'm gonna make this bigger. How long am I streaming for? Maybe like around 1 or 2 more hours. It's not gonna be as long as last time because I like have some other things that have to be done, but I can go for a while, I suppose. By the way, 5,000 when? Okay. Yeah, this whole thing was fun. We can get rid of it now. I'm actually very, very surprised that I didn't get a wrong answer on that. Very surprised. Okay, so the basic idea is we have a lot of people here. Each person is... we have groups. I do have school, but not on Wednesdays normally, which means that today is fine to stream. That's the reason today is the only day I can stream, because I normally have school on the other days. Dedication? Okay, well, that's arguable. My dedication was more explaining how to solve, like I had the solution, but the dedication was about explaining how to solve it than anything else. Because explaining like a knapsack transition is hard. Yeah. Okay, so the number of requests from visitors, then end lines follow. Right. So you have a bunch of tables. Each table has some sort of capacity. Let's say, for example, 4, 6, and 9. And you have a bunch of people. Each person has a size. Wait, each group has a size. And, for example, 10 and 50. And then 2 and 100. And 5 and 30. You can match any person to any table as long as there are enough seats at the table to fit all the people. Dynamic programming is daunting. Did you have trouble solving basic problems? I did. Dynamic programming took me like months to learn in USCO training. Mostly because there weren't enough like problems to make it solidify. And I just like didn't know what I was doing for a very long time. Yeah, okay. How many months? Maybe like there's something like 1 or 2. Like I was actually trying to learn it. It's hard. Yeah, DP is not an easy concept. Like it's not easy to learn. I'm trying to do this stream to give a bunch of examples, but no matter what, it's going to be hard to learn. That's kind of it's like hard. Doing Spodge, but struggled to come up with your own solutions. That's kind of I don't know. I feel like if it's that case, you should put more time into it. Because it's better to like have the thought process of trying a ton of things and like I mean eventually something's going to work. Something has to work. So the more time you spend thinking on a problem, the more like the better of a thinking process you'll have in general. That's the way I see it. Bitmass DP. This problem, the third one, was Bitmass DP. You can see that on the previous stream if you want. And the previous stream is both on my channel and in this description. I'm not sure if there are any other Bitmass DP ones, but I know that one is. Okay, back to this problem. So the basic idea is, let's say we have a matchup like this, where we, first let's sort the tables, or let's sort the groups and the tables by their, like, values. Or by the people that they can require and also store. And apparently that cut it off for some reason. Say we have something... Where did that go? There was like a piece of purple that just disappeared from here, supposedly. How long do I try and solve a problem? That depends. Could be like anywhere from an hour to multiple days sometimes. That was my philosophy for USCO training, at least. Div 2D? Yeah, I can try that after this. If I get through these quickly enough. Okay, right? So the basic idea is you have something like this, and you basically want to assign as many of these to tables as you want. So let's say you have some assignment like this, right? Then, like, this assignment sort of like crosses the paths of these two arrows. So therefore you assign the higher one to a lower one, and you assign the lower one to a higher one. But if this is possible, then you could do the exact same assignment, but you could assign the lower one to the lower one and the higher one to the higher one. And this may in fact be better, because then it leaves you like more sort of freedom. Like you can assign this higher one to more possible things. So the argument is, for any like consider some optimal configuration. Like consider the optimal configuration where you have some sort of cross paths like this. Then you can instead change that optimal configuration to not have cross paths. So therefore, because you can do it like this, if there exists an optimal configuration, which there does, then you can change it so there's an optimal configuration that doesn't cross paths. And what that means is that you can solve for the optimal configuration where you assign the values sort of in sorted order. So like when you assign this value to something here, then that means anything you assign to this one will be after this one. That's the idea. So you could instead do this like this, and you will assign them in sorted order. Now this is easier because now you have something like this. Wait, is div2d the graph one? The one with like clicks and stuff? I hate that problem. That problem has terrible limits. Like most solutions were like very, very close to the time limit, wasn't it? Will I drop to blue/purple? I will not. Actually, I might unintentionally, but not for that purpose. Okay, but anyway, now that we have this in sorted order, that means that we can squeeze some information down to like a single part. Say we know this, and we know the last thing we assigned was this one. And we know we assigned it to this. Then it automatically means that like whatever we assign here, it has to be after this one. So we don't care about specifically which ones were assigned, we only care about the position of the last assigned one. So that's cool because what it means is that the only information we need is the current the current group we're on and the current thing we're trying to assign to. Because we know that once we're here, we can't assign to anything before here, and we're only going to assign to anything after here. So that's the only information we need. And therefore the state is simply dp on the group and the current table we're at. And then we can define it like this. I'm going to try and do a recursive formulation here to try and like switch it up a bit. Is equal to the dp of either we assign this group to this table, plus the cost of this group, or the what is it? The price of this group. So p. All right. Sorry, this should be group -1, table -1, plus p of the group. Because this is just simply like, we assign this group to this table, so we decrease 1 from both of them because both of them are used. And actually it's the maximum over all this, because these are the possibilities for things we can do at this point. Or we can go into the previous group, or we can go into the previous table. And so the reason we can sort of like do this sort of like subtracting 1 magic is because essentially like either we make this assignment or we made the assignment with some other group or some other table, or possibly both. But if we have to decrease in like both of these, then we'll eventually do so. Like we can do like a -1 here and then a -1 here and then a -1 here. And so it'll eventually find the previous pair that we used. But this makes the assumption that we've used all groups up to this point or not used them. And we've used all tables up to this point. So this recurrence is very similar to edit distance. Or I think that's what it is. Except now we're finding the maximum instead of the minimum. Is it edit distance or like longest common subsequence or something? Oh, and this transition is only possible if the C of the group, like if we have enough people, the size of the group is less than or equal to the table size, R table. Right, okay. So now we implement this. Will this be 1005? And then we make an array for the tables. Let's see. So first, I have this very basic thing that just reads into a pair. Reads the first one first and the second one second. It's like quite intuitive. Then read in the tables. This would be M. Wait, what? Oh. So read into N, read into the groups, read in the, okay. It's not guaranteed that either of them are sorted, I suppose. So we sort the groups, and we sort the tables. It should be K. Then let's define this DP function. So we've used N tables and K groups, or N groups and K tables. Then we just simply do that. This is going to be memoization. You can do it in any way you want, though. You may also try like the basic table, the basic, like the well-known form of DP, like the one where you just do it in the loop. That's also possible. DP 0, 0 equals 0. So let's see. First case, if we're out of bounds, return some like negative huge number, like 10 to the 9th. If we know this value, return it, because we don't want to recompute values. And so then we have 3 possibilities. Return dp and k equals max. First possibility is f m minus 1. Oh wait. Actually, let's just do this. If, let's see. So if it's groups I dot first is less than tables, should be n. Okay. Then what that means is that, all right, it should be less than or equal to. That means we can assign this group to this table, essentially. Then what we can do is v equals max, v f n minus 1, k minus 1, plus the value we get from it. V equals max, v f of m minus 1 k equals max, v f of n, k minus 1. Then we memoize it by setting dp and k to that. And this -1 is fine because none of these values are ever going to be -1. Should be F. Oh, we have to print the values. Okay, that's kind of annoying. Alright, printing the values is kind of annoying. But let's just first compute the value first. I forgot we had to do that. Okay. So first we'll compute the values, and then I'll demonstrate how to recover the actual things from a transition. Right. How's this gonna work? Okay, what am I doing wrong, first of all? There's something that's going wrong here. Not entirely sure why. So let's see. Just print everything. Ultimate debugging strategy. And then something's happening. Somehow we like don't take this one. But I'm not sure why. 0, 1. What? Groups end up first is less than or equal to tables. Okay. So 0 and 1. Our group 1 and 1 is 30 somehow. How would it be 30? 1 and 1. But 2 and 100 should be first. Oh wait, this should be m minus 1. Okay. Yeah, right. So if n is greater than 0 and k is greater than 0, then we consider the previous ones, because those are the ones we take. Or actually, because we're 0 indexing, that's why. That would make more sense. Now we have 80 somehow. I'm not even sure how that's possible. Wait, how is that even possible? There's no way that could happen. What? Okay, 1, 1, 30. There's no way that could happen. That should be this. Yeah. Whoops. That makes sense. That would be how that could happen. Yeah. Okay, now we get 130, which is fine, but now we have to recover this. And so the way to recover this generally is to store sort of a parent array. So like, we know we have 3 possibilities, right? And so what that means is either we took it or we came from one of these. So say we have this and we want to figure out how we got this answer. So then either we came from here, in which case, like, this was our previous state. We came from here, or we came from here. So we can store what we came from, essentially. We can say that if we did this, we did like action 0 or something. If we did this, we did action 1. If we did this, we did action 2. And then we store the action we took, and then from here we can figure out what the previous state was by tracing back our actions. So this is generally called like a parent array or something. So let's see. We'll start with this, and then now we have to see specifically, we can't take the maximum anymore. We have to see, does this improve the answer? And if so, then set the parent to that. So this would be if val is greater than v, then v equals val, and parent nk is equal to action 0. So if n is greater than 0, val equals f m minus 1 k. If val is greater than v, v equals val, and the parent of this is action 1. We do sort of the exact same thing here. If k is greater than 0, then consider m minus 1, k minus 1, and the parent is action 2. And then we just do this. This will set a parent everywhere except 0, 0. So now we sort of just like do this annoying thing where we gotta do some stuff. So vector we need the indices. Oh, I hate this problem. We need the indices of the values we took. And it's fun. Okay, well we want the indices sorted by. Okay, this is how we do this last part now. We want the indices. How have I gone this far down? Okay. We want the indices sorted by value. For example, we have like this 50 in index 0, and we have this 10, and then this index 1, and this 25, and this index 2. Then we can sort of create these pairs of value and index, and then we can sort this list of pairs. Then when we have the things in sort of value, but we also have the indices that we want. So that's what I'm about to do here, and it's going to be very annoying, because now there's like even more information we need to store. Group vals, and the same thing for tables. Group vals I equals make pair groups I dot first the value and I. And we can sort these two. And we do the same thing here. Just tedious implementation, it doesn't add anything to it. Table vals I equals make pair table. No, wait. Yeah, tables I and then I. And then sort the table vals plus k. Now we basically store the operations we did. So cur group is equal to n, current table is equal to k. Now while cur group is greater than 0, or cur table is greater than 0, what we're doing here is we're basically starting at the ending state and we're retracing our steps. So if, let's see, if the parent of current group and current table is equal to 0, then we took both. So ops.push back. So let's see, it would be table values current group minus 1 dot second for the index. And the other one would be table values, or wait, it would be, no, this would be group values, and the other one would be table values. Slightly going insane. That's second, minus minus cur group, and minus minus cur table. Else if par cur group cur table is equal to 2, no, 1, then that means the last time we just went back a group, so just do that. Else minus minus cur table. And then to restore the answer, we do this. And we print add 1 because we're 0 indexing. I'll be done with this problem yet. Okay, books to improve competitive programming. Well, good knowledge of C++ is good. There's some thing here you can use, I think. Like there's a CSS book or something, CSES. Yeah, you can try this. I heard this is pretty good. Hopefully that works as a link. I'm not entirely sure if it does. Can you see that or not? Or do I have to put it in the description because YouTube's... Okay, cool. You can't see it. Hopefully. 3, 2, 2, 1. Yep, so we print the answer. Somehow I took all of them. Not sure how. What? I have no idea why that happened. See out cur group. What? What happened? So we're at 3, we're at 2, we're at 1. Somehow we took all of them, even though it doesn't make sense. I don't understand how this happened. I guess we should make this like -1e7 or something to make it so it's not. So even if we come from the. This doesn't make sense. What the hell? Okay, I guess we're printing the parents now. Well, no book will help you improve your problem solving skills. So what you have to do to improve problem solving is like problem solve. Like you can go to Code Forces or actually CSES. Like the problems go with the book, so you can try that too. There are a lot of things you can do, but like if you know stuff, the best thing to do then is to solve problems. That's the only way to. That's definitely the best way to improve problem solving is to do it. I'm not sure what's happening. What does it think is going on? Like the parents are 1. What does it mean? I have no idea what's happening. What? Why would that do that? Like it's not printing the thing. What is it not printing? Oh, wait. That kind of makes sense. Okay. Yeah, okay. That makes sense. Yeah, that's the problem with recursive, actually. Like, you rely on the, Oh, this is annoying. Yeah, okay. So the reason I have to do this first is because, like, this parent thing doesn't work if I don't compute the values. So that makes sense. And the fact that the printing was out of order was an indicator of that I was doing the things in the wrong order. Okay, now it still doesn't make sense. 2, 130, match 3 with 3, and 2 with 2. Okay, that works. Hopefully that's enough. I don't like this problem, so I want this to pass. But yeah, that's the basic idea. Do some DP, restore the answer. Get wrong answer on test 3, apparently. Or not. My answer on test 20. What does that mean? Yeah, you can definitely start CP without like prior knowledge and stuff. What the hell is this? Have I done some like indexing stuff or something? How is it wrong answer on test 20? How did I pass 19 tests? What happened? NCIPI. Right, okay. So let's just like sanity check everything, I guess. So read in the value, read in the group, make the pair sorted by index. Then do the same thing for the tables, make it sorted by index. Sort the groups, sort the indices, sort the tables, sort everything. Initialize the DP, make the operations. Compute the function. I guess the function would be wrong. Then the current group in the current table is K. Walk backwards through the parent thing. And then from here we print the operations that we do. And ideally it doesn't like screw us over somehow. Alright, so if n is less than 0 or k is less than 0, return some massive negative value. If dpnk is not equal to -1, return dpnk. Maybe there should be an even bigger negative value, like 1e10. That could be it, because otherwise it could like possibly take like the worst of... Actually, that probably shouldn't change anything. Yeah, okay, never mind. Well, something's wrong here. So if both are greater than 0, then that means we could possibly take this as a value. And could take this as a value. Then if this is better than what we have, set it to that, set the parent to this. If currently like n is greater than 0, then the previous value we can consider removing this one and then going backwards on it. Then we set the parent to action 1, and same thing for here. We set the parent to action 2. And I'm not exactly sure. That is annoying. So if this parent is 0, then make the operation with like this and that. And if this parent is 1, then go back in the group, otherwise go back in the table. Maybe I think there might actually be some other issue with sorting. Okay, maybe the issue is that like if there are tables with the same value, oh that's so annoying. If there are tables with the same value, but like different like benefits, like for example a 50 and like a 10 versus like a 50 and a 1000, then like maybe it's giving it the wrong value. Sorting by ignoring this might make it so we take the 10 instead of the 1000. I think that's what the problem is, and that's so annoying. But not luckily, we don't actually care about that, I suppose. Okay. Yeah, I guess that's what it would be. That's what we did, right? Yeah. Does that fix it? Get wrong answer somewhere else. Okay. We got that problem. We have 3 left with my limited time frame. I'm not sure I'm going to be able to cover all of them, but I will try. Let's see. Okay, first I'm going to go to the bathroom. I'll be back. Alright, be right back again. Make my own sort of cover screen. And like a check mark. I don't know. I'll see you guys in a second. Alright, I returned. Hello, everyone. I'm not sure what I'm going to be able to do. I have like maybe an hour and a half left, so I'm not sure if I can get through the rest of this. But I'll try. Solve div2d. Maybe. If I have time. I mean, I want to finish this mashup. That's the ultimate goal for this stream. I'm not sure if I can, but I can try. So I'll do this one. I mean, is div2d dp? It like isn't, right? Div2d is this like graph one where you have to find a click and stuff, isn't it? It's like very annoying. It's very annoying because the time limit's 1 second. I have 3 left. We'll see. We'll see. We'll see. Right. Okay, well the idea for that problem is, the idea for the div2d is that you just like, you remove all nodes that have degree less than k minus 1. Because otherwise it's impossible. Like you can't use those nodes ever, so get rid of them. And then while you still have nodes that are of degree less than k minus 1, get rid of them. Now all nodes have degree at most k minus 1. Yeah, I could link the invite too. That's true. But whatever. Actually, I'll cover that problem like after. Since it's like I can't just explain it without any sort of visual because it's a graph problem. Sure, I could link the mashup actually, it's kind of smarter. Although I'm not sure if this huge like invitation. Actually, wait, maybe that'll work. Let me try that. Does that fit? It does fit. Okay. Okay. Cool. So, all right, whatever's going on here. Do I have notes? I do not. Okay. So with this problem M, recently Arena arrived to one of the most famous cities of Berlin, the Berlatov city. There are N show places in the city, numbered from 1 to N, and some of them are connected by one-directional roads. The roads in Berlatov are designed in a way such that there are no cyclic routes between show places. So it's a tree. Initially, Arena stands at the show place 1, and the endpoint of her journey is the show place N. Wait, is it a tree? How does this work? There are no cyclic routes, so it could be a forest. Wait, what? Oh, is it directed? Okay, it's directed. Never mind. So it's a directed acyclic graph. My bad. Initially, Arena stands at the show place 1. The endpoint is the show place N. She wants to visit as many show places as she can. However, her stay is limited and she can't be there for more than T time units. Help her determine how many show places she may visit during her journey from show place 1 to show place N with the time not exceeding T. It is guaranteed that there is at least one route from show place 1 to show place N, such that Arena will spend no more than T time units passing it. Is this DP? How many show places she may visit? Okay. Memory. That's annoying. Alright, so this is my interpretation of the problem statement. I hope it's right. You're given this directed acyclic graph, which you can represent kind of like in weird representation-ish. And you have this node 1, and you want to get to node N. And so acyclic means that there are no cycles. So like, there's some order in which you can visit the vertices so that like there are no cycles or something. So for example, like this. I mean, like you can sort of assign every vertex a height, and then this height would be like. Actually, this is a bad example. Do it like this, I suppose, and then this would work. Yeah, okay. I guess so. Whenever I try and think about an easy problem, do I guess the solution? I mean, sort of. That's the power of intuition. Like, for easier problems, they just kind of, like, go down quite easily because most of them can either relate to previous ideas or it's just intuition, like, powers through it. Like, there will come a time where you just see a problem, you look at it, and you just know the solution instantly. Whether it be a topic or some sort of math thing, but that will be what intuition does. That's kind of what happens with when you get to a certain point. Which is why sometimes it's like hard for me to explain how I solve easy problems. Because most of it's just experience, and that you can't really teach. Let me make this a thing too. Add this as an edge. Okay, right? Now we're interested in, so each edge has a weight. Let's just assume these edges are weighted like with whatever. Then you want to find essentially the longest path from 1 to N that uses no more than T units. Okay, so the fact is n is small. N is like 5,000, which is nice, because what it means is that what happens is that like we can go here. How will this work? Okay. There's something with topological sort here, but I don't want to explain it like that. So I'm going to try and explain it a more intuitive way, I guess. Say we're like here or something, and we want to find the longest path that uses like not many time units to this. Well, n is small. So what we can do is, in sort of in the DP fashion of storing some information and keeping track of like others, what will we want this state to be? First, the state has to include a vertex. That's just always how it works. So a DP of vertex. But then because n is small, and this is a directed acyclic graph, meaning there are no cycles, any path is going to be at most length n. So even though the time values are massive, we have 10 to the 9th time values, like there's no way we can ever store that in terms of anything. We can instead store the path length that we use. So we're interested in getting to this vertex, having visited this many vertices in the past. And the information we store is then... one second. The information we store is that... Yeah. The information we store is that, like, we store the minimal time, or like the minimal total path length to get to here. So we fix the vertex and we fix the length, and then we're interested in the least amount of time we could have used to get to, for example, here, having visited 2 vertices. So minimum time. Now this is nice, because say we know this information for like position n, then say we know t equals 9, and then we know we can get with 1 vertex in 3 time units, we can get with 2 vertices in 7 time units, and we can get with 3 vertices in 10 time units. Then we know that we can't have a path of length 3, but we can of length 2 because 7 is less than 9. And so in total, what we do is just we compute this information over all vertices, and then essentially we can use that in a DP manner to compute it for future vertices. Now the hardest part in doing this is figuring out what order to do this in. Because, like, here's the problem. This is not an array. It's harder than an array. So we're computing it for this. Then, like, there's 3 separate vertices this can depend on. This can depend on this, this, and this. And so, like, I don't think this is a good example, actually. I'm trying to demonstrate how this could be hard. Sure, I guess it wouldn't be. Never mind. I'm kind of wrong. I think it wouldn't be... Recursive kind of like takes the cake here because it's nice. So there's not exactly a great iterative way to do this. The way to do this with iterative DP will be to find this thing called a topological sort. And what a topological sort is essentially like it's an ordering of the vertices such that every vertex, like every edge, goes from a lower number to a higher number. So for example, it would be like this. This would be a topological sort like this would be invalid because this edge leads from a 7 to a 6, and 7 is higher than 6, so that's bad. Like, we want it so every edge leads from a lower number to a higher number. So for example, this would be a good topological sort. We can do something like this, And the reason this is nice is because in sort of iterative DP, this topological sort will give us an order to process the vertices in. Because it guarantees that once we get to a vertex, everything ahead of it guarantees that when we get to a vertex, everything that comes before it will already have been processed. That's again the whole point of finding an ordering for iterative DP. Everything before it has to have already been processed. And once we get to this point, so that's one way to do it with iterative. The other way is with recursive, and with recursive it's nice because we don't care about the order at all. So we can totally ignore this whole topological sort thing and instead just like let the recursion do the work. Oh wow, we hit 5,000? That's cool. Let me see. Let me open YouTube then. There we go, we did it. So yeah, as people may have been saying, there is going to be some 5,000 subscriber special. I will announce what it is later. In fact, I will announce it in both the Discord and this community tab, so you should check back on this at some point. It may or may not be soon. But like, I'm gonna announce it here, so if you check this and it's like there, then it'll be there. Okay, I think this is worth updating the sub count again. Because why not? Yeah, let me get rid of this, and then we can do this whole part. So now we have 5,000, and we're even closer to memory limit exceeded now. How cool is that? Yeah, casual double in subscribers. That is indeed true. Okay. So basically with recursion, this becomes very easy. What is the rating of this? Judging by the number of solves it has, I would guess either, here, let's find out. I'll open incognito, and we'll see. 1,800. Okay. So it's not terrible. Alright, so basically this DP value is VLen is equal to the minimum of all like DP of a previous vertex. That means a vertex that has an edge to this one. And len minus 1 plus the cost of taking this edge. So for example, n would rely on this state, and then it would be, and then the extra cost would be, for example, this weight. That's one possibility. We consider all the edges that have this. We consider all the edges that go into this vertex. Okay, in terms of transitions, this is actually quite simple. And then to find the answer, we just check all possible things for the last node and see which ones work. So let's do that. We have DP of 5,005 and 5,005. Is that going to work? 5,000 squared times 8. It's barely going to pass. This might actually cause MLE now. Wait. Okay. 26 times 3 times 8. It's barely going to pass the memory limit. That's fun. Okay. So first, read in the values. So now, for I equals 0, I is less than n, I plus plus. No, m. This means we have an edge from u to v. Alright, I'll read chat in a sec after this. This is the most important. Like, we read an edge from U to V, but we're really interested in how many edges go to this. Which means we kind of want to reverse these edges to say that we have an edge from this one to this one. Because we're only considering it when we're actually at this node. So we kind of like reverse the graph. We reverse all the edges like so. Edges v dot push back. Okay. What happened? So, if you want to make your way up in code forces, yes, problem practicing is definitely the best advice. Past mistakes. Past mistakes, I think my biggest mistake was getting too like wrapped up in it. Like taking this thing too seriously, honestly. Because if you take it seriously, you're gonna get like stressed and freaked out during contests, and it's gonna like totally screw up your mentality. But if you go in it not caring, like it's the best way to think about it, because then you'll just be able to focus. You'll be able to think about the problems instead of thinking about rating and like being scared and everything. So I would say that is a good thing. What do I use Notepad++ to prove a point? To prove a point that IDE doesn't matter. Yeah, I do have the pin message, but I didn't have it last time. That's the key. It told me like recently that I had this option now, but it wasn't there before. Okay, I'm gonna write this code and sort of like be more silent about it. So now, VL length. Let's see. Yeah, this should be turn 3 1. Sure. We need to print the path here, right? Oh, we do need to print the path. Come on. What is it with these problems and restoring the answer? First, f x dot f len minus 1. So if len is equal to 0, if v is equal to 0, return 0, return 1/16, because that'd be invalid. So now we assume len is like greater than 1, then if cost is less than best, best equals cost, and previous v len is equal to x dot first. Is it bad practice to write top or bottom DP? I mean, not really. In general, it mostly works for everything. Certain problems, like, it's harder to do it a certain way. Certain problems, it may actually be impossible, but, like, by the time you get to those kind of problems, you'll be comfortable enough so that it's not that hard to recognize. And 0. I am 17. Yeah, I just use light mode because I don't like the feeling of dark mode. Like, it's kind of like claustrophobic in a sense. It's just like personal preference. If it blinds all of you, then that's for the better. So you're welcome. Yeah, I'm 17 right now. Currently. Subject to change in the future, hopefully. Cur equals prev. What would be previous of current and it would be pause cur. Then we decrease the length by 1, so decrease cur. And then 0. Then we put them in reverse, so we have to like we constructed the path from reverse, so we have to reverse the whole thing. Well, they want spaces or okay. That's fun. Actually, I should make these ints. This is not going to pass memory limit. Oh, come on. Can't use prev because it's a reserved word. Are you kidding me? Okay. This is not going to pass the memory limit. And that's fine. I will figure that out as soon as I make this work. 1, 2, 4. 1, 2, 4, 6. Okay. I have to make these ints, because otherwise it's not going to work. But to make these ints, it's like even more annoying, because now I have to make this not long. Let's see, so this can be min. What should I make it? Like the value t? Yeah, I guess I don't really care. I guess I don't really care what it is, as long as I make sure that if it's greater than the limit, then I store that. So that's supposedly fine. Like, it just needs to not overflow, that's the point. Okay, let's see if it does overflow. I'm not being careful right now, so it could get wrong. It could very well get wrong answer, and that's acceptable, I suppose. Wow, that is a high time usage. What the hell? How is this so? Oh, yeah, it's n squared. Okay, that makes sense. Right. What's in the chat? Let me check everything. Why did I use, wait, why did I use 3 and 9 before? Like, I basically just picked an arbitrary big number. Like, it doesn't matter what the big number is, as long as it's big enough that it's bigger than any plausible value that could possibly, like, mean something. Is getting state by writing recursive DP and taking the variable parameters a good practice? Yeah, that's fine. I mean, I'm doing it right now, it just passed this problem. In some cases, it's a lot easier to write recursive than iterative. Like, for example, recursive handles the computing order for this. But if you were to do iterative, you would have to do it on a topological sort, which is, like, annoying. Don't do that if you don't have to. Yeah, -3, or 3 and 9 was basically infinity. That's what I meant it as. Um, 2D DP answer, 2D DP questions. I see people making tables, but can't we solve, like, directly? Not sure what you mean by that. Like a direct relation would be like. What do you mean? What do you mean by direct relations? I'll check that after. Is it possible to get the answer if you have to do iterative with compressed memory? I'm not sure. That seems hard to do. I'm not sure if that's possible. Like direct relations would be DP, right? Typing speed like 100 or something like that, like around 100 maybe. Connected component DP. I don't know what that is. Wait, let me see if I do know what that is. Is this something I know? It's a non-trivial trick. Yeah, I don't know this. I wouldn't be able to explain it because I've never seen it before, unfortunately. What? Why did I get rid of the formatting? Wait, this text like has no color for some reason. That's kind of black. Okay, there it is. Alright, so we got that one. We have 2 left. Supposedly this one is also tied for the hardest one, so I'll try this now. And I'll also repin the message and everything. What'll this be? N. I'll pin that one. Coolio. You're given a matrix A with n rows and m columns. Each cell contains an integer in it. You can change the order of rows arbitrarily, but you can't change the order of cells in a row. After you pick some order of rows, you traverse the whole matrix the following way. Firstly, visit all cells of the first column from the top row to the bottom one. Then the same for the second column. What? Firstly, visit all cells of the first column from the top row to the bottom one, then the same for the second column, and so on. During the traversal, you write the sequence of the numbers on the cells in the same order that you visit them. Let that sequence be S1, S2, SNM. So that's fun. Look, it's not that I didn't know how to pin messages before, okay? It's that I literally couldn't do it. I don't know what you mean. Like, I didn't have the ability to before. It wasn't like I couldn't figure it out. Alright, okay. Let me try and explain this problem, I guess. I see a way to do this. This is actually like, this is a separate form of bitmask DP that I think is quite cool. And in fact, this may be exactly what some of you wanted, so that's perfect. This mashup is like surprisingly versatile. Like it has kind of everything in a sense. Maybe I'm missing some things, but I see that it has a lot of things that are useful. Well, div 1As are hard. That's true, I guess. Alright, let's explain this problem. So you got this, like... Why would n be 1? So you have this, like, this group of cells. Like so. You have this group of cells. Wait, how would this work? Okay, I'll use the second sample, I guess. You have a bunch of... You have this, like, matrix. Each matrix has a bunch of rows. Alright. Trying to illustrate this in a non-terrible way, but, like, let's see how to do this. So basically you have values like this. 9, 9, 10, 8, 5, 3, and 4, 3. And in one move, you can sort of like, you can move this row anywhere you want. Like so. You can rearrange the rows however you want, but you can't rearrange the columns. That's what it is, right? You can rearrange the rows. Okay. So then, and then what you do is, so this traversal is kind of like this. You go down like so, and then back up to here, and then down like so. Or it's sort of like you go here, and then you go here. And then I guess you write all these numbers in a list. So you'd write 9, 10, 4, 5, 9, 8, 3, and 3. And then essentially what you want to do now is you want to, this looks terrible. Okay, in 0-1 knapsack problems can we visualize them without making tables? Well, kind of. I mean, like the table is only to store the answers that you've computed. That's all it is. You're just keeping track of what you've done. I mean, in another sense, it is a function, kind of. Like, it is a function of a certain number of values and a certain number of weight that you've taken so far. And then that function relies on previous values of that function. And to optimize that function, what you do is you store the values of the function that you've computed already. And that's what the table's for. So it's kind of necessary, but you don't need it to, like, understand the way the recurrence works, I suppose. Okay, right? So you're going to write all these numbers out, and then you're going to take, like, essentially you want to maximize the minimum absolute difference between any two values. So for example, this difference is 1, this difference is 6, this difference is 1, this difference is 4, this difference is 1, this difference is 5, this difference is 0. So the maximum so the minimum value is 0, and therefore this arrangement is terrible, so we want to do better. But that's the idea of it. Right. So the key here is that the number of rows is less than or equal to 16. Now that's the key. Because now we can do some sums like some coolses stuff, you know, the coolses. And the way we do the coolses is, wait, didn't I have, okay, no, I have two 2000s. I guess this is the other 2000. But the way to do this is like so. You say you've put the first k rows down. And whatever the cost is for these rows, like, it's not that important. What, does that have some other meaning that I don't understand? I just said it to sound weird. Like, say you put all these rows down, right? And so what we want to do now is we want to kind of, like, we have this cost between these two, and we have this cost between these two, right? But these costs is just like, it's summarizable in a number. This number x is the maximum, or the minimum absolute difference between any two adjacent values. And we'll kind of ignore the fact that we also have to, like, compare these values too, like these values between the bottom row and the top row, because we can handle that later. But like, say we put the first k rows down, then we have some cost x. Then we put another row down. The only thing we care about is the previous row, essentially. So then when we put this row down, now we have k plus 1 rows. K plus 1. And then we continue until we put all the rows down. Right. So if we were to sort of summarize having put these rows down, what we care about is which rows we put down so far. Actually, we care about which rows we put down so far and the previous row we put down, because that's going to determine the next cost. So we have some sort of state that looks like this. dp of which rows and the previous row. And in terms of handling this cost, the cost between the last row and the first row, what we can also do is we also have to store the first row in the state, otherwise it's not possible to, otherwise we can't like determine the final cost. So we store the like which rows we've taken, the previous row and the first row. Previous and first are simple, they're just numbers. And which row can be represented like so? We can create some sort of like vector that represents whether each row has been taken or not, instead of having a list of rows. Like, for example, like so. So this means the first row has not been taken, the second has been, the third has been, the fourth hasn't, the fifth has been, and the sixth hasn't. And then this would be our state, for example. And then when we want to figure out if a row's been taken, we just like ask the vector, like, has this been taken or not? Right? So that's simple. But like at the same time, vectors are annoying. Let's do better. We have at most 16 values. And notice that these values are either 1 or 0, which means that they're like kind of like binary values. So what if we just compress this entire vector into a single number? Like a binary number that represents this value. And then to ask if something's been used or not is the same as asking whether whether this bit is set or not, which we can do with some bitwise magic. And because this is less than or equal to 16, this final number is going to be less than or equal to 2 to the 16th. And that's the total number of possibilities we have for this state. So this is called a bit mask because we use like a binary number to represent other types of information. And so the strategy in general is called bit mask DP. Then the transition is simply put down a new row and then ask how does that affect the cost. And specifically, like when we put down a new row, then we're kind of interested in what's the minimum absolute difference between any two like corresponding elements in this row. So like sort of a problem is that this is a lot. Like this is very much a lot because m is like less than or equal to 10 to the fourth. So if we naively compute this transition each time, it's going to be something like O of 2 to the n times n cubed, because we need 2 to the n times n states. And then this transition, there are n possible rows we can put down. So this is 2 to the n times n cubed. But then computing this is going to be also 10 to the fourth. So let's figure out what that is. Quick back of the envelope calculation, or just like using a computer. 2 to the 16th times 16 cubed. That in itself is bad, and we have 4 seconds to compensate. But if we stick on a 10 to the fourth, like there's no way this is going to work, right? Just look at that number. It's so big. But like, again, we don't have many rows. And what we're really interested in is, given some row A and some other row B, what's the cost between it? So the idea is that we don't have to compute this cost every time. In the beginning, we can compute the cost between row A and row B. And that'll be it. We can pre-compute it, and then we can use this sort of as a lookup table, so we don't have to do 10 to the fourth operations each time, since we've already done it at the beginning. So the total complexity comes out to just 2 to the n times n cubed, because we already know these values. How are TMUS-DP problems? I'm not sure. I've never actually used that site, so I wouldn't know. But I know like people like Umnik have praised that site before, and he's like, what is he now? He's 5th in the world right now. So it's probably good. Yeah, it's probably good. Let's see. Okay. How are we doing in terms of everything? I'm not excited to code this, but we gotta do it, so let's do it. Please tell me we don't have to restore the answer. Oh, thank God. Okay, we only need to print the value, not the rows themselves. Thank God. Okay, awesome. So the basic idea with these cost arrays is that cost 1 is going to be the the original cost, the minimum of the absolute differences between the corresponding column values, and cost 2 is going to be specifically the cost from like this, having this row as the ending and this row as the beginning. So therefore we have to compare this element with this one, and we have to compare this element with whatever would be here, and so on. So that's cost 2. So the values are 189. Mat I k minus mat j k. Then Actually, let's just do it like this. Cost 1ij equals this. Then cost 1ij is just do that. Seems good. Then we do the same thing for cost 2. What the hell? We do n minus 1 here because we're comparing this one with the one ahead, so we exclude the last index. Cost 2ij. And most of these values are going to be redundant, like we don't need to compute ij and ji. But for convenience, it's like whatever. So this is min cost 2ij. Abs mat I k minus mat j k plus 1, the next value. Now we do the dp of 2 to the 16th. We can just do 17. Now, how do we do these transitions? That is a question. It is in fact a good question, and one that I do not know how to answer. So that's fun. Yay. We have okay. Doing push dp here is definitely the way to go. Because otherwise, like, we can't easily determine what the previous and the first rows would be, I guess. What is infinity? Sure. Actually, I want to maximize this, so we can just make it 0. So in fact, none of this was necessary. Okay. Now first, we check if this state makes sense. So this state makes sense if, first of all, the rows aren't equal. Actually, no. Never mind. The rows can be equal, that's fine. Actually, no. If we have more than, like, n is greater if... Okay, what? So LO, we do -1 because we don't care about the final state. How'd this work? So, like, the number of rows is equal to this magic function called built-in pop count of mask. And what this does is it simply just counts the number of set bits. Actually, it could be long, doesn't matter. But the point is it counts the number of set bits. Then if n rows is if n rows is equal to 1, no, wait. If n rows is greater than 1, no. Sorry. If n rows is equal to 1, and therefore I should be equal to j, or I is not equal to j, then we continue. Otherwise, if so, then, like, we have multiple rows, but some row is both the first and the last, and that doesn't make sense. So then, also, like, this row must have been a previous row that we already took, otherwise it doesn't make sense. And the way to do that is to check essentially, we can check if some bit is set in this mask by asking, is the mask... Here, let me illustrate this. Say we have this mask like so. Then we start off with this 1. Then, say we're interested in this bit, which is like 2 from the... which is like 2 from the right, kind of. Then we shift this bit over by 2. So we end up with this number 100. This is called a bit shift. And then we ask, is the bitwise AND of these two numbers greater than 0? If so, then that means this bit is set in this one and this one, and it's automatically set in this one. So it basically just finds out if this bit is set in the number. So that's how we check if something's in the mask. So if mask, bitwise AND 2 to the I, then... And we check the same for J, because like the rows we say are the first and last have to be valid rows. Otherwise, nothing makes sense. So now we know we have a valid state, I think. There may be more things to check, I'm not sure. But then now, new row, let's just say K is the new row. Then we have to check if this bit is not set, mask and 1, 2 to the K, because we can't take a row that we've already taken. So then the current cost is cost 1 of mask. Alright, new state is equal to mask bitwise OR 2 to the K. Because now if this bit is not set, then it will set this bit by doing bitwise OR. Set this bit by doing bitwise OR. Then this value is cost 1 of, not the mask, that doesn't make sense. It's the cost of the previous row, which is J. And the new row, which is K. Then cost equals min. It'll be dp mask I j v. Am I going to MIT? That's a good question. I will find that out later, I suppose. The cost is the minimum of dp mask I j and v. Alright, so now the new state is dp of new state. The first row is still I, but the most recent row is now K, equals the maximum of dp new state I K, and the current state, or just cost actually. Just like look at this, man. We have a streak of 9 brackets right now. Oh my god. Okay. So now we essentially consider all the possibilities of the first and last, and ants equals max ants, and the minimum of the dp of, this should be 2 to the n minus 1, because this is, like, it's the state where all of the rows have been used. It's the full bit mask, essentially, where everything is a 1. And then this would be I, J, and the cost 2 between I and j. No, and also, let's see, so mask, is it worth having 0 be like a thing? Does this work if I do that? Like dp of 0. I guess I should make it so like dp of 0, having no bits set is kind of annoying, so let's do it otherwise. Equals 0, I is less than n, I plus plus, dp of 2 to the I, where I is the first row and the last row is equal to 2 and n. That should work. I'm doing push dp here, so I exclude the last state. Like, I'm pushing this state out to new state, so I exclude the last state because there's nothing to push it out to. And having dp with like no bits set is kind of annoying to handle transitions for, so I just explicitly like ignore that. Do not print an answer. I don't even print answer. Nice. There's no way this works first try, so I will try with optimism, but who knows. 5, 0, 3. It's possible. It's possible. Who knows? I don't really care about wrong answers, so we'll try it. How much do I practice IOI style tests? Not that much. I used to do like a ton of Yusuko and try and like grind through all of Platinum, then I sort of gave up on that. But I did a lot of OI practice before. Now I sort of don't. Okay, it's getting past tests. That's scary. Alright, I guess I'm wrong. Fine, I'm wrong. It worked first try. My bad. This is going very smoothly. And I think part of it is because I'm being so elaborate in explaining what I'm doing. Like, this is sort of like the rubber duck debugging effect. If you explain what you're doing and you, like, say it out loud and it doesn't make sense, then you'll realize that. I guess that's how it would work. Was this the other 2000? I suppose it would be. I open it in incognito so it, like, shows the tags. Oh, come on. To open the original problem. And then from there, I can do that. Is Yusuko enough for ad hoc tax? Maybe bronze? I'm not sure. It's kind of like changed recently. Yusuko Silver has gotten a lot of like ad hoc style stuff. Yeah, this is 2000, but it's also a Div 3, so who knows. I am not in college. I'm in my last year of high school. I feel like you could argue Yusuko is enough for ad hoc. But I mean, you can also like go for variety, stuff like @coder and stuff. Yeah, Yusuko is definitely shifting. You're given an array A with n elements. Each element of A is either 0 or 1. Let's denote the length of the longest subsegment of consecutive elements in A, consisting of only numbers 1, is f of A. You can change no more than k zeros to 1s to maximize f of A. First line contains two integers n and k, number of elements in A and the parameter k. Second line contains an array of zeros and ones. So you could do this with 2 pointers, but that's not the point of this. So let's not do that. Let's do the DP way. And is there a DP way? That's the question. Not entirely sure if there is a DP way. Well, you have to print the value? Oh, come on. Seriously? What is with this? I have to figure out how to solve this with DP somehow. And we have to print the values. How fun is that? Why would you have to print the values here? This doesn't even make sense. Bitmask DP is kind of hard to understand, I agree. It's probably better to like learn it explicitly first, although yeah, I mean it's kind of satisfying to solve those kinds of problems. I don't know, that's my opinion, but it doesn't come up that often. So it's not that big of a priority, but I mean you could try the problem. It's more up to you whether you want to or not. How would I model this as a DP problem? Alright, well this is problem O. This is the final problem. Final problem of the mashup. Probably final problem of the day. I should go soon. So I couldn't get to custom requests. This took longer than I thought it would, but perhaps in a future topic stream we can do more. Sir. I'm genuinely struggling to solve this with dynamic programming. So this is problem O. And you have a line of zeros and ones. Let's say you got like 1, 0, 0, 1, 0, 1, 0, 1, 0, 1. And some like, so essentially you can like pick two, you have some number k, like for example k equals 2. And you can pick two zeros and then change them to 1. So you can say like this is 1 and this is 1. And then you're interested in the longest like streak of ones you can have. So the longest group of ones that's like all together. And that's the idea. And I guess the way we would model this is kind of the same as the other DP problems. The other DP problems of like the similar like streak of ones. Like this isn't even DP, it's like more two-pointed. But say you fix some ending position, like for example I, then f of I is the longest streak ending at I. What age did I learn to program? Something like, I started Python in middle school, but it was like not that well established. So I would say like the C++ type of thing that I actually know came from learning Java, and that was in freshman year in high school. So that was like 14 or 15 or so. I'm not a fast. I sucked at learning Python. Like I was terrible at Python for the first 2 or 3 years. I am 17 now. F of I is longest streak of ones ending at I. Alright, okay. I honestly have no idea how to justify this as DP. Could I just call this 2 pointers and call it a day? Like, I don't... Do you have any DP ideas, chat? I don't know how to do this. I guess you can model it like this. Or actually, you can model it like, F of I is like start position of longest streak of ones. And you can observe that if you move from I to I plus 1, and let's say the starting position is here, then like... Oh, I didn't repin the thing. Oh, whoops. That is a mistake. Thank you for noticing that. So like the basic idea is, if this is the best you can do, then if you move over here, then you're gonna have like more zeros. So there's no way you can do better and move over here when you have more zeros to deal with. So which means like as this goes right, this is also going to go right. So the idea is that f of I is less than or equal to f of I plus 1. Yeah, you could binary search too, that would work. Binary search 2 pointers, any sort of thing. Oh, wait, that would make sense. Okay. If you do binary search with prefix sums, that would be DP, I guess, because prefix sums themselves are DP. Alright, I'm not going to do that, though. 2 pointers is so much nicer. But, okay, the way to do DP is to, like, do the prefix sums, like, let P of I be number of zeros on the values 1 to I. And then, like the count of zeros on some range L and R is equal to P of R minus P of L minus 1. And so this is DP because P of I is equal to, it is DP, what do you mean? It's as DP as Fibonacci is, and everyone uses Fibonacci as DP. It's the Boolean condition of AI equals 0, which means that this is 1 if true, and 0 if not. Plus P of I minus 1. It's definitely DP. Look, it literally relies on previous values, man. That's what DP is. I mean, if you really want, you can do it in like some weird kind of like stuff that goes on. But like P of I relies on P of I minus 1. Even though the tree is like not a tree, it's like, even though the recursion tree is not a tree, it still kind of like makes sense. And I mean, if you want to make it DP, you could do the standard trick of converting the parentheses to brackets, like P bracket I, and then now you're working with an array, and then it's definitely DP. Depends on how you implement it, actually. But anyway, that's probably why they tagged it DP. I'm trying to justify why they tagged this problem as DP. But the basic idea is now, say you have some starting point and then you have some array like after this, for example. Then you're interested in the condition, like what's the longest subarray that has less than or equal to k zeros, starting from here. Alright, I guess I can do this. I guess I can do it like this, why not? So we're interested in the longest subarray that has less than or equal to k zeros. But like, when we get a longer subarray, like the number of zeros is only going to increase. So therefore, if we have some subarray that has more than k zeros, then every longer subarray is going to also have more than k zeros. And if we get fewer elements, then we're always going to have fewer zeros. So if this subarray has fewer than k zeros, then any like subarray of that is going to also have fewer than k zeros. Which means that like if you consider like the ranges where it works, like all of these are valid up to a certain point, and then it like and then it starts being bad. And then it starts being bad off until infinity. So you can binary search on this point where it's the largest point that still works. That's the idea. Yeah, I forgot to pin it before. Alright, but basically the idea is you can binary search from each starting point. Okay, I guess I can implement that, because that's, to finish off the DP sort of style, that's what I should do, I guess. Why not? So we can do binary search. And then I can also stick that in the stream. For L equals 0, I equals N plus plus. I'm not doing 2 pointers. I'm gonna drop the 2 pointers part and do it explicitly DP, just to be annoying. Length, comma, start. Because we have to construct the answer, so we need to know the starting position that's the best for us. Yeah, okay, it's not exactly a DP solution. The DP part is computing these things called prefix sums. Where basically, we're looking for the sum of zeros on a range. We're looking for the number of zeros on a range. And if we can find the number of zeros on a range, then we can binary search on the largest range that has at most k zeros. So the way we can compute this is we compute the number of zeros on like every prefix. Like for example, we compute it from on the first 1 element, then the first 2 elements, then the first 3 elements, then the first 4 elements, and so on. Random colors here, right? And then say we want like the range 2 to 5. Then like this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So we're interested in this prefix. But then we sort of have this excess. So what we want to do is we want to subtract out everything that we don't want. And essentially that means we can subtract out, so currently we have 1 to 5. So if we subtract the interval 1 to 1, then we end up with the interval 2 to 5. So essentially we subtract this out, so we cross this out, and then we get exactly the interval we want. But the point is, this sort of prefix sum thing, where we compute the prefix, that's the DP part. Because the prefix sum is simply the previous prefix plus whatever the current element is. That's what that is. And then from there, we do the binary search. And that's fine. dpxy max length of contiguous ones with y zeros in between them. Won't that like bn squared? It's like a lot. I mean, yeah, okay, that's another valid solution that works, but for the constraints, it doesn't. I assume people tagged it because there's an actual solution with it. Like, you can say everything is brute force, but you can't submit brute force to everything and have it work. You can say everything is FFT. You can model integer multiplication as FFT, and that would work, but like nobody does that, so don't. And then I think you can do like, I mean, okay, yeah, it's stupid, like dumb things that aren't worth thinking about. So let's do the prefix sums now, because that is worth thinking about. We have at most 3 times 10 to the 5th. So pref 0 equals 0. Pref I plus 1 equals pref I plus the Boolean condition of AI is equal to 0. This will be specifically 1 if it's 0 or not if not. And this is equivalent to also saying not AI in bitwise magic. But this is just asking, is it 0 or not? If so, add 1. Otherwise, not. Next idea is to simply at Coder Beginner contest. I'm not sure. I might Twitch it. Actually, I'm not sure. I kind of don't have more time this week because next weekend is gonna be busy. There's like round 685 on the weekend, and then after that, there's one on Code Chef that I'm doing on Sunday. So kind of just like I don't have much time to do things. And that's usually the reason why I skip contests, either because of school or because there's just other stuff going on that makes it impossible. So in short, probably not, unfortunately. What was I doing? Right. Fix the starting point. Then L equals I, R equals N. If, let's see. So, let's do like get sum or something. L R, return pref R plus 1 minus pref L. This will give us the number of zeros. If get sum LM is greater than K, R equals, let's see. Let's think about this binary search here. So we query this point middle. If this is too many, then we have to go into this range, and therefore we cross this whole thing out. So if this is too many, then R equals M, else L equals M plus 1. That's how it works, right? Yeah, R is exclusive. So then best equals max, best make pair, what would it be? So it'd be R minus I, and then I. We store the length and the index. So then, wait. Cout best dot first, endo equals 0, I is less than n, I plus plus. Then the range we have is the range of best dot second, the beginning, and then best dot second plus best dot first is the range. This side is exclusive. This side is inclusive. The other is exclusive. And then we ask if it's within the range. Best dot s is less than or equal to I, and I is less than best dot s plus best dot first. Cout 1 else cout AI. That's what we want, right? And we say we get 5 somehow. How do we get 5? How does this happen? Also, there's a separate way to handle a binary search like this. Like you pick the range and then you ask about the middle. And basically what you consider is you consider like the final position where L plus 1 is equal to R. And therefore, like, if this is valid, then you're going to jump to this one. And if not, then you're going to jump to this one. And so, like, you can sort of figure out the whole way to structure the binary search and the indexing based on only considering the last thing you're going to do. But anyway, that's a topic for something else. Like, this isn't that big a deal. You just do it. Like, if this is valid, then it's gonna go, yeah. Okay, but why? Should it be -1, I suppose? R is exclusive. Why does that work? Or is R not exclusive? No, it still doesn't work. Okay. What? What have I done? How does that get to 7? Why does 2 get to 7? I have no idea what the easy binary search is. Also, why does 2 get to 7? I'm doing the prefix sums wrong somehow. Okay, this I definitely don't understand. What? How's the range on 6 to 7 -1? What exactly is it doing? Okay, that shouldn't be a problem. Like, what is 2 to 5? Two to 5 is 2. And my get sum is assuming 0-based indexes, but then it like uses the 1-based prefix sums. I don't know. I'm doing some sort of indexing wrong. Like, read in the values. No, it's not R equals n minus 1. My binary search is exclusive of R. Like, the current range we're solving for is inclusive of L, exclusive R. parallel best, right? Then prefix of 0 is 0. Does it mess up the other one? What is it doing? Does mess up that one too. It's like off by 1 or something. I don't know why. That is annoying. So somehow 3 gets 10. Okay, I guess we're gonna trace this. Cause I love that. Why not? Oh, that's why. It should be I and M, not L and M. Yeah, whoops. Otherwise that would make things too small. What? Where the hell did I go? Okay, there we go. Yeah, okay, that's a bit annoying. Alright, well, that is this whole mashup done in like... Okay, the problem was that what I want to do with this binary search is I want to figure out what's the longest, like, prefix of this sort of subarray starting at I. Or what's the longest subarray starting at I that's, that has at most k zeros. But the problem was when I was modifying L, I was also changing the starting point. So what I had to do was make this I, which is fixed, instead of L, which could change. Okay, and again, the DP part was doing this prefix sum sort of thing. If you missed that, you can rewind or something. Alright, well, that's this whole mashup. I don't have the energy to do anything else, but that is that, I suppose. What else did I get wrong? Oh, right, it was that, like, that thing. That annoying sorting. Alright, yeah, this will conclude the stream. I hope you enjoyed. If you missed some of it, this VOD will be up, like, later. So, it should be fine. I'll put timestamps and stuff. It'll be great. Alright, enjoy life. I'll see you all.